We had it up here earlier.
It's first order.
It's first order. So again, I have to tell you the rate law or ask you to derive it, but we had it up here for this exact reaction earlier, and we were using just first order rate law, KCA. And remember that we have K, 3, 1, 1, inverse minutes. Okay, so chapter 4, stoichiometry. What do we know about the volume? Liquid phase, so the volumetric flow rates are constant in a CSTR. So the concentration then is equal to the flow rate of A divided by the volumetric flow rate, which is just going to be the initial volumetric flow rate into the unit. So do I know that? Kinda. This is where the problem gets a little bit tricky because they don't describe the inlet flow rate in a convenient manner. So we'll try to do that over here. So let's find so this is the volumetric flow rate of that first inlet. Okay? The flow rate of OA, right, of that first inlet divided by, so this is just from rearranging this concentration equation that we've been using. Concentration is flow over volumetric flow rate, so volumetric flow rate is just flow divided by concentration. And notice that FA naught A is equal to FA naught. This flow rate is got to be the same as that flow rate in terms of species A, because this was pure water, right? Think back to the problem statement. It said mixing in pure water of some volumetric flow rate. Okay? So that means these are the same. So now I can put this in terms of FAO. And the concentration here is given. So I'll put in the numbers directly, and you get the number we just found, 7.67 pound moles per minute divided by 1 pound mole per cubic foot. Does everybody see how we did that? All I'm doing is a material balance on that mixing point. So you guys have all had that class. You all aced it, so no problem. All right. So the units just rearrange, right, and we get that the volumetric flow rate of this stream A, little a, is equal to 7.67 cubic feet per minute. And what did the problem statement tell me about the volumetric flow rate of the other inlet stream? That they're equal. So what's the total volumetric flow rate?
15.34.
I guess. You guys are good at arithmetic. Yeah. Yeah, it's just the sum. Okay? So yeah, that's the trick. You guys should be used to this by now. Chemical engineering problems almost always have some little tricks, little wrinkles. There it is. They didn't just tell you what the volumetric flow rate of the feed was. They thought that would be too easy. So they put in a little wrinkle, but it's solvable. Just remember that sometimes you might have to do material balances on mixing points that come before your unit. Okay? It's nothing you can't handle. Alright, so V, I erased the equation that it came from, but we had an equation for V up here. 15.34 cubic feet per minute divided by 0.311 inverse minutes. So that's K, that's just V divided by K. And then the conversion, 0.8, 1 minus 0.8. Okay, 197 cubic feet, which he also has here for the curious. It's about 1,500 gallons. Which, if you had a cylindrical tank, he also has one here, about 5 wide. 10 feet tall. It's a pretty big tank. But remember how much it was producing, right? 200 million pounds a year. So it's not like it's producing just a little bit. All right, any questions? All right, let's look at another example. If I have two 800 gallon CSTRs, all right, so in another example, continuing this one. Two 800 gallon CSRs are available. And the total volumetric flow rate to the system is 15.34 cubic feet per minute. Now we want to show that a arrangement with the reactors in series yields a higher conversion than a parallel arrangement. Okay? So yeah, it's obvious to you guys by now, I hope, that a series arrangement would be better, but let's just work through it. So there's my total volumetric flow rate going into the system, right? Now what do I do? If I'm drawing the parallel unit.
Just split the stream.
I have a splitter. How much is going up versus down?
Let's say equal.
Same, which is what?
1/2 V0.
I have some volume here, right? And we know that that's 800. That's in the problem statement. And then we come out, and we are coming out at some conversion of X. Anything different about these two units that you've been told? No, right? So we can assume that they're operating at the same temperature, meaning that the rate constants are the same, meaning that we can write out we'll jump straight to that equation, which we showed on the board earlier today. Do we know tau?
Yes.
Yeah. So what's tau?
800 divided by 1/2, 15.34.
Yeah, first in terms of symbols, and then in terms of numbers. 800 gallons. Here is why it's so important to put in the units, right? Because what we have here is 1/2 times what? What are our units for V naught? Where the hell did it go? There it is.
2 cubic per meter.
Right? So we've got to convert gallons per cubic foot. And I have that here, 7.48 gallons in a cubic foot. So our units, we're left with minutes. That makes sense. It's called a residence time. And what's K equal to? Somebody say 0?
Wait, no.
Yeah.
Yeah, you asked what K was, and you were talking about tau times K. It's 0.311.
Units cancel, and you get 4.34. So now coming back here, x is equal to 4.34 divided by 5.34, which is 0.81. Any questions? That one's pretty simple, right? What if this wasn't so easy? You guys know how to derive it, okay? That's what we did to start the class. You guys know how to derive it. If it's not a first order reaction, this is going to look different. But you guys know how to deal with that. All right, now let's look at in series, and then we'll be done. So this first reactor, it's the same equation that we just used, right? It doesn't know any better. So it's just x1 equal to tau1 k1 over 1 plus tau1 k1. Now tau has changed, right? Everybody see why? I'm no longer splitting the feed, right? So now tau is equal to 6.97 minutes. That's half of what it was before, which should make sense. If I double flow rate, residence time is half as much. And so tau times K is also half as much as what it was. It was 4.34. So coming back here, it's 2.17 divided by what? 3.17, which is 0.684. Okay? So we're not done yet. That's just this one. Now let's do the second tank. Going back to the mole balance, we get FAO times X2 minus X1 divided by the rate of consumption. You can put that in terms of concentrations. And then we can put it in terms of volumetric flow rates. So now just taking that form and rearranging and substituting in our definition of residence time, we get, move this down. Okay, so I can rearrange that. So it's just 0.684. This is still 2.17. Doesn't mean it always will be. It's still that this time because we haven't changed the volume, right? They have the same tank size, 800 gallons. And so you get 0.90. So you get a higher conversion, as you might expect. Notice that we didn't jump straight to here this time, right? We didn't have that already conveniently derived on our notes. So we just had to go back to the material balance, put things in terms of concentrations, recognize that the volume is constant, and that makes this pretty trivial. And so, yeah.
Could we use the equation you derived earlier?
Yeah, I was about to get to that. The last thing I'm going to put on the board is that this is the same as if I took x2. Remember we had an equation for xn, and that's equal to 1 minus 1 over so that's 2 now because it's the second reactor. But remember that that only works if they're the same volume, right? So not a lot of times that they're going to be the same volume. So know how to do it coming all the way back to here. Because this equation works even if they're different volumes or if they're operating at different temperatures, right? Because the rate constants could be different. I'd have to give you both rate constants, of course. Okay, that's it for today. Next time we'll talk about tubular reactors. This was all CSTRs. Now we're going to move